Okay, let's start. So we were proving things about countably infinite sets, and we proved that n cross n is countably infinite by, like I gave you two bijections. Checking that this is a bijection is easy, that one is more tricky, but these are both bijections, so this is countably infinite. An easy corollary of this is that if you have two countably infinite sets, then their Cartesian product is countably infinite, because you can just use the fact that this is countably infinite. Like find bijections between n and a and n and b, then construct the bijection from n cross n to a cross b. Okay? So the next theorem we're going to prove is that subset of a countably infinite set is at most countable. Lemma, a subset of a countably infinite set is at most countable. Why is this the case? Let's see. This is, let's say that this is my set X, and this is countable. This is countably infinite, so there is a bijection from natural numbers to X. Okay, so these are the elements of X, and we're going to take a subset of X. We want to show that this subset is at most countable. It suffices to show that this subset is, I mean, there's a surjection from n to this subset. Or maybe we do this proof differently. Saying that this is at most countable means what? This is either finite or countably infinite. So I need to prove that this is either finite or countably infinite. Okay? So let X be a countably infinite set and Y be a subset of X. Now there are two cases. Well, never mind. I'm not going to split into cases. I'm going to do the proof the way I wrote in the notes. Okay. Nah, never mind. Case 1. If Y is infinite, sorry, if Y is finite, then it is at most countable by definition. Okay, that's part of the definition of being at most countable. Okay, if this is a finite set, then it's already at most countable. So what we need to show is that if it is infinite, then it's actually countably infinite. We need to show that if Y is infinite, then Y is countably infinite. Okay? Now, let's fix a bijection from n to x. Okay? Let's fix a bijection. How would you construct a bijection from n to y? What you would do is, okay, let's say that 0 is mapped to some element of y. Then you should map 0 to that element of y. Let's say that this element, 1 maps to this element, so you should map 1 to that element. If some element of y, like, okay, I'm trying to count the elements of y. I'm trying to label them by natural numbers. What I'm going to do is I'm going to try to count the elements using these labels when I can do that. So what do I mean by when I can do that? Let's say that the picture is like this. This guy is mapped by 0, so I'm going to send 0 to this guy. This guy is mapped by 1, I'm going to send 1 to this guy. Let's say that 2 is mapped to something outside y, but 3 is mapped to this guy. Okay? Sorry. Let's say that 2 is mapped to something outside this, but 3 is mapped to some element inside this. Then what I would do is I'm going to say, okay, 2 is mapped to something outside this, but 3 is not. So I'm just going to send 2 to this guy. Or do I want to do the proof like this, or maybe I want to do it with a surjection. Let me check how I did this. Yeah, I'm going to do the proof like this, okay? So let's let B be some element of y such that B is of the form f of k and k is the least natural number such that f of k is in B. Is in y, okay? So what I do is I look for the least natural number which under f is mapped to something in y. On this picture it's 0, okay? On this picture my k is 0 and this is my element B. Now by recursion, define the following function. By recursion, define g from natural numbers to y as follows. 0 is mapped to that B, okay? Now pretend that I have defined g up to some natural number n. Here is how I define it for the next guy. This is f of, maybe I should use I, where I is the least natural number such that f of I is in y minus f of 0, f of 1, up to f of n. Okay? So what this does is the following. Again, I found the least natural number which is mapped to some element of y. In this case, it's 0. So I take this to be my 0th guy. I mapped 0 to this guy. In order to find the next guy, what I do is the following. I look at the previous values of this function. I take those guys out of y. I have some subset of y. I find the least integer I so that f of I is mapped onto that. So let's see. I take this b out. Then I found the least integer which is mapped to some guy in the remaining part of y under f. In this case, it's 1, okay? Because 1 is mapped to this guy. So I'm going to send 1 to this guy. Now I take these two out. I take these two guys out. I look for the least integer which is mapped to some guy in y under f. Now the image of 2 is outside this, so 2 is not that guy, but 3 is. The image of 3 is in this guy. So I'm just going to map 2 to this guy. Basically, the elements of X are already labeled by natural numbers. I picked this subset Y. I'm trying to count Y in the exact same order, but instead of using the labels, let's say 0, 1, 3, blah, blah, I'm basically relabeling. Like I say that this is the 0th element, first element. Now the second element is outside, so I go to the third element. Third element is inside, so now this is my second element, and so on. So this is basically relabeling elements of Y in the order induced by F, okay? Now, where am I using the fact that Y is infinite? Since Y is infinite, an induction argument shows that. Now, since Y is infinite, I can always find, well, I don't actually even need, yeah, never mind. Why does this definition make sense? Why does this always exist? You need to actually argue that this is always non-empty for all n, and it requires some induction. And moreover, you can prove the following. G of S of n is different than G of k for all k between 0 and n. You see, you're choosing some element this is not supposed to be F, this is supposed to be G. You're choosing some element that is not already chosen. So automatically this is going to be an injective function. Okay? So, yeah, we have this. Now, it is easily checked that, I'm not going to do this, easily check that. That shows that this function is injective because at every stage you're choosing something not chosen. And you can easily show that this is also surjective. Why is this surjective? Take any element of Y. Because, let's say that you take this Y0. Because F is a bijection, there is some natural number K mapping onto this guy under F. By construction, Y0 has to be mapped by some N, which is at most K, okay? You can easily show that at most K stage of this construction, that Y0 will be mapped onto. So, this guy is a bijection. Okay? Basically, what I'm doing is I'm doing something very simple, but somehow I was able to write it in a complicated way. I'm trying to count element, like X has a natural ordering here. 0th element, first element, second, third. I'm just trying to count elements of Y in the exact same order. 0th element, first element, well, the second element is outside. The third element is inside. Now this is my second element of Y. And I look for the third element and fourth element and so on. So, is this proof understood? Is the idea understood? Okay. Now, using this, we can show, using this lemma, we can show the following. Theorem. Let A sub I in N be an index system of sets such that these guys are all countable. A sub I is countable for I in n. So I have countably many countable sets. Theorem is that their union is countable. Okay? Indeed, yeah. When I say countable, I mean at most countable. Sorry for this. Now, for each I in n, again I'm going to use the axiom of choice. Choose. What do you know about countable sets, at most countable sets? Natural numbers surject onto these guys. So for each I, choose a surjection. I'm going to call this G sub I from n to A sub I. Again, the more formal, the more correct way of writing this is as follows. For each I, construct the set of look at the set of surjections from natural numbers to A sub I. That set is non-empty because this is at most countable. That's non-empty for all I, which means that by axiom of choice, I can choose one element from each of these non-empty sets. So that's basically I'm doing. For each I, choose one surjection from natural numbers to AI. Again, I'm just going to say that via axiom of choice. Then, the map, the function, from natural numbers to the union of these guys given by f of mn equals g sub mn is a surjection. Why is this a surjection? Pick an element in the union. Then it's an element of one of these AIs. Let's say that you picked an element from this. Let's say that it's an element of A7. Which means that if you look at all the values F70, 71, 72, 73, 74, so on, one of these guys will have to hit that element, because G sub 7 is a surjection from n to A sub 7. That's exactly what we're doing. Fix some m. As you change n, you hit all elements of A sub m. Which means that if you also change m, you're going to hit all possible elements in this union, possibly multiple times. This is why I said this is a surjection. You can only deduce that this is a surjection. Thus, there is an injection in the other direction. There's an injection from this union to n cross n. And so, maybe I should finish it in one line. This union is countable as it is equinumerous with its image. If you look at the image of this guy, it's a subset of a countable set, so it's countable by the lemma. Maybe I should add that. Which is countable by the lemma. So this guy, the image is a subset of a countable set, so it's countable by that lemma. Which means what? This guy is equinumerous with a countable set, so it's itself countable. Okay, so countable use of countable sets is countable. Again, I'm going to emphasize the fact that this proof cannot be done without the axiom of choice. It is consistent, if you just drop the axiom of choice, it's consistent with the rest of the axioms that countable union of countable sets is not countable. Indeed, drop the axiom of choice, add some other axioms, then real numbers, which we're going to see as uncountable, can be written as a countable union of countable sets. Yes, you can do that. Of course, that's happening in a different set theory. The point is you need AC to do this, because in order to try to enumerate this, you need to choose a surjection. I mean, people think that I'm just going to imitate the proof which was over here last lecture. I'm just going to list the elements of A0, okay? I'm going to list the elements of A1. And I'm going to list the elements of A2. Now, in order to enumerate the union, I'm just going to use the Cantor pairing function. Well, yes, that would work if only you could enumerate the elements of these guys. And you can enumerate them, but the problem is you have to decide how you're going to enumerate them. There are multiple ways to enumerate this. So you have to somehow fix a way to enumerate all of these sets at once. In order to construct this table, you need the axiom of choice, okay? So, that's that. And what else do I want to prove? Oh, yeah. There are some consequences of this theorem, easy consequences. Okay, let's start with let me assign two exercises. Show that if A and B are countable, then A cross B is countable. I'm not saying countably infinite this time, I'm saying countable. This is easy, no more difficult, not more difficult than the previous one, and this is the exercise I really want to assign. For every natural number n and countable set A, the set of functions from this natural number to A is countable. Or maybe I write this in here. The n-fold Cartesian product is countable, okay? It's the same thing. Corollary to this lemma. For every natural number and countable set A, the set of sequences over A of finite length. Now we learned what a sequence is. A sequence is a special kind of function. A sequence of length k is a function from k to whatever set your sequence is over. So a sequence of length n over the set A, it's a function from n to A, which means that this is the set of all sequences over A of length n. If I change n from 0 to infinity, if I just take all possible finite values of this, this is the set of all sequences of finite length over A. And this set is countable. Use the exercise and the theorem. Exercise and the previous theorem. This immediately follows. Why? You have countably many different countables. You have countably many different sets, each of which is countable. By the theorem, countable union of countable sets is countable. Okay? So, we have that. What else do I need to assign about countable sets? Do I have more exercises in my mind? No, these two are fine. Okay. I have some exercises in mind, but I don't want to assign it right now. We can talk about this later. Let's continue the lecture. Now, let's talk about uncountable sets. Before we start talking about this, let's introduce some more terminology. We shall write, okay, let A be two sets. We shall write this and say the cardinality of A is less than or equal to the cardinality of B if there is an injection from A to B. Now later when we introduce cardinal numbers, we're going to give a different meaning. We're going to give a different meaning to this notation, but it's not going to be really different. Okay, that meaning we're going to assign will be consistent with this notation, okay? But for now, this simply means that there's an injection from A to B. And we shall write instead of less than or equal to, we shall write this if the cardinality of A is less than or equal to cardinality of B and there is no bijection between them. Okay? Remember, this meant that there's a bijection between them. This means that there's no. So this simply means that there's an injection from here to here, but there is no bijection between these two guys. Okay? And in this case, we say that the cardinality of A is strictly less than cardinality of B, but I don't want to write that. It's just too many words on the board. Now, what we're talking about, uncountable sets. Do uncountable sets exist? The answer turns out to be yes, and historically speaking, this is the birth of set theory, this theorem. Well, not this theorem, but okay, kind of this theorem and the surrounding other stuff. We're going to prove Cantor's theorem, which says that uncountable sets do exist. Before Cantor, people thought that there is this absolute notion of infinity, like there's only one infinity. Infinity is infinity. There's one absolute notion. It turns out that this is not the case. There are various degrees of infinity. And it was Cantor who first realized this. And he had different proofs of this. The proof I'm going to do is not his first proof. Okay? He used a method called diagonalization. I'm going to tell you why it's called diagonalization in a second. He had different proofs of the same, he had 3 different proofs, I guess, maybe 2, but I believe it was 3. And he used diagonalization in all of these. So they all had the same spirit. I'm going to do the version I personally like the most about power sets. So here it is. Theorem. So this is Cantor's theorem. This is important. This is important as in last year when I taught this course, I asked the question state and prove Cantor's theorem in all of the exams. I asked the same question over and over again until students were able to actually do the proof and understand the proof, okay? This is important. The reason this is important is it's not the statement, it's the technique called diagonalization. In logic, this technique is generalized to many different, maybe I should say, okay. I was about to say it's generalized to many different versions, but that's not actually true. There's only one argument, but it's applied to many, many places. You use the argument I'm about to describe in many, many places. Okay? The argument called diagonalization. Anyway, let's take the Cantor's theorem. Cantor's theorem says that for any set X, there's an injection from X to power set of X, but there is no bijection between these two guys. Which means that if you put n for X, this would mean that there is no bijection between power set of natural numbers and natural numbers, meaning that power set of natural numbers is uncountable. Now let me do the proof. Let's do the easy part. Consider the map from X to power set of X given by this. An element of X goes to the singleton containing that set. This is a subset of X, so this is a map. This map is an injection. Clearly. Well, if two singletons are the same, then their elements are the same, so this is an injection. And so I have that the cardinality of X is less than or equal to the cardinality of the power set of X. We need to show that there is no bijection F from X to the power set of X. Okay? Assume to the contrary that we have a bijection. Now, consider the following subset of X. I take all elements in X such that they are not members of the subsets they are mapped to. Now, I'm going to finish the proof formally like in a second, then I'm going to show you why this is called diagonalization, what this has to do with diagonals, and why is this important. So consider the subset. This is, first of all, a set. Why? X is a set. I'm taking the elements of X which satisfy a property written in the language of set theory. So by axiom of separation, this is a set. Such a set exists. Okay? Now, this is clearly a subset of X. Now, since F is surjective, I have a surjection. There is some little w in X such that this little guy maps onto W. Because this is a subset of X, so it's an element in here. This is a surjection, so something maps onto this. Okay? But then I ask the following question. Is little w an element of big W? This is a subset of X. This is an element of X. I can ask this question, whether this is true or not. If this little w is an element of big W, then by definition of big W, little w is not an element of f of little w, which is big W. So if A happens, then not A happens. Okay. Now assume that W is not in big W. Well, big W is f of W, so if W is not here, then W is not in f of W, but then by definition, it has to be in W. And this is a contradiction. P happens if and only if P does not happen. Thus, f cannot be, there is no such f. Thus, there is no such bijection. If you analyze this proof, you will realize that we actually proved something stronger. That not only there is no bijection from here to here, there is no surjection from here to here. I mean, the only property of f that leads to a contradiction is that this is surjective. So what we're really proving is there is no surjection from x to power set of x. And this is sometimes what's called Cantor's theorem in some books. Like if you pick up some random set theory book, it is likely that what they're going to call Cantor's theorem is the theorem that there is no surjection from x to power set of x, because that's the real essence of this proof. The rest is, like, this is unimportant. But I want to state it like this. Now, why is this called diagonalization? Okay, quick question. How many of you have seen the diagonal argument before? Okay. Let me show you the original diagonal argument. Then I'm going to show you why this is called diagonalization. I put the natural numbers over here. I construct this grid. Now, I add, and this goes to infinity in both directions. This goes to infinity, this goes to infinity. You have an infinite grid. I ask you to do the following. Think of any 0, 1 sequence. Think of 0, 1 sequences. Fill these rows with 0, 1 sequences. So for the first row, you're going to do this. I'm just making up stuff now. I'm just going to fill this some way. The dot 1 1 0 1 1 0 0 0 0 1 0. It goes like this. Pretend that you fill this table with some 0, 1 sequences. My claim is the following. No matter how you fill these rows, I can always find a 0, 1 sequence which is not contained over in here. How am I going to do that? I'm going to look at the diagonal of this table. The diagonal gives me a 0, 1 sequence. 0, 1, 0, 0, 1, 1, and so on. I'm going to flip the diagonal. I'm going to turn zeros to ones, ones to zeros. Now, I claim that this sequence star it can't be found on any row. Why? Pretend that, okay, take this guy, try to put this somewhere over here. Pretend that this sequence I call star, it's somewhere over here. Okay? this row and this diagonal will have to intersect somewhere. Now, let me write this 1, 0, 1, 1, 0, 0, blah, blah, blah. At the intersection, what's going to happen? I constructed this guy, I constructed star by flipping the digits of this diagonal. Which means that this cannot be 0, because if this was 0, well, I need, like this is on the diagonal, so in order to construct this, I need to flip this digit. So this has to be 1, but it can't be 1 because if it were 1, it has to be 0 as well. The point is, the kth digit of, the kth digit of this sequence differs from the kth digit of this diagonal for every k. So they can't possibly meet at the kth row because the kth digit of this is different than the kth digit of this. Now this is called the diagonal argument. What you're doing is, try to understand what we're doing in here, like in a more general perspective. We have, you're giving me a list. I'm doing something so that the resulting object is made different than anything on that list, okay? Now, it's obvious why it's called diagonal argument, right? You're diagonalizing, this process is called diagonalizing. You're diagonalizing every row. Diagonalizing meaning that you're just making sure that the thing you're constructing is different than the thing in this row, and this row, and so on, okay? Now, this is also a diagonal argument. What we're doing is the following. Here's my set X. This may be uncountable, but pretend that I have this infinite ability to list elements of X, okay? Maybe it's uncountable. Maybe I can't enumerate them with natural numbers. I can do that with ordinals, which we're going to learn later, but forget about this. Pretend for now that this is countable, okay? So that it actually works on the picture. So these are the elements of X. Over here, list some subsets of X, okay? So I'm going to list a subset of X. I'm going to list another subset. I'm pretending that it is countable, but as you will realize from the proof, it has nothing to do with countability of the set. So I've listed all of X, and I listed empty set. Now over here, I'm just going to list this subset. And over here, I'm just going to put this guy. Over here, I'm listing subsets of X. Corresponding to these subsets, I have elements of X. I'm looking at the following subset. The subset consisting of guys which are not in the subset they're labeled with, okay? What does this guarantee? Okay. Say this guy, this X, is a member of this guy. It's a member of W. If X is a member of W, it is not in here, right? It can't be seen in here by definition. It's not supposed to be in the set it's sent to. So, some element appearing in this set guarantees that that element is not in here. X1 is in here, so it's not in my W, this is in W, this is not in W. So some element appearing in W guarantees that it's not in the subset it's mapped to. Now, if you collect all these guys together, what you're guaranteeing is you're basically, in a sense, diagonalizing against all subsets of the form f of x where x is in this guy. The point is, okay, over here we guaranteed that this guy is not seen on the kth row by flipping the kth digit. Over here we are guaranteeing that this is not on this list by making sure that anything in here, well, by making sure that this is different than all possible f of x, which satisfy this property, okay? Okay, that was, I think, a bad explanation. I could have, like, okay, it's not a bad explanation, but this is still called diagonalization, but you don't see the diagonal here. There's no diagonal to be seen. Over here, you actually see a diagonal. Over here, you don't see that, but the idea is the same, okay? By requiring certain conditions, you guarantee that a certain subset is not on the list. Anyway, yeah, take all the guys that belong to W, okay? Maybe I should draw more stuff. Take the subset of X, take this subset of X. If this were somewhere down in the list, we would get a contradiction. Why? Because if this were on this list, there would be some element mapping to that. Let's call it alpha, or in this case it's gamma. Well, if you ask the question, is gamma in here or not? Well, if gamma is in W, then it has to be not in here, so it can't happen. But gamma can't be outside as well, okay? So, is this proof understood? Proof of Cantor's theorem. Okay. Now, a corollary of this is that power set of natural numbers is not countable. Proof, take x equals n in Cantor's theorem. By the way, you might have realized that this is also true for finite sets. I mean, you already knew that this is true for finite sets because if this has n power n elements, but this proof also shows that there's no bijection between them. Anyway, this is not countable. Exercise, show that the set of functions from natural numbers to natural numbers is not countable. Use the fact that, remember that was an exercise I assigned a lot of time ago, which said that the following is true. There's a bijection between power set of any set and this set of functions from that set to 2. Okay? So, show that this is not countable. So, uncountable sets exist in, like, we don't have enough time, but let me talk about the third proof. Yeah, I think Cantor has 3 proofs. We have this, the usual diagonalization with 0, 1 sequences. The other one is the one I did. And the third one, the first one, historically the first one Cantor did, it's about, it doesn't look like this at all. What he does is, And then you would be surprised where all this came from. This came from trigonometric series, okay? He was dealing with some analysis problem, and he was dealing with trigonometric series. At some point, he decided to do the following. He's considering these closed intervals, which are somehow avoiding, bless you, closed nested intervals which are avoiding countably many guys. So what? No, I'm taking that back. That's not true. Okay. Historically, the first diagonalization argument, what he did was, I forgot the details, but he was choosing closed intervals, okay? And then these closed intervals were avoiding certain points. And that avoiding certain point part is basically corresponding to this diagonalization argument, like flipping bits. And then he showed that, what he showed at the end was this. No matter how you try to list real numbers, if you list countably many real numbers, I can always find a real number which is different than those guys. What you're doing is, you give me a list of real numbers, okay? You list it, this is a real number, this is a real number, this is a real number. I'm going to find a closed interval not containing this. I'm going to find another closed interval not containing these two. I'm going to find a closed interval not containing these three. I'm going to find a closed interval not containing these four, and I'm going to choose these intervals so that their intersection is non-empty. Okay? There's a theorem called Cantor intersection theorem. I don't know if you know that. If you're working, like, let's work with real numbers because it's complete. You have to have your metric space complete. If you have closed nested intervals, if you take their intersection, that intersection is non-empty. That comes from the completeness of real numbers. So what he did was basically use that fact, like he's avoiding all these real numbers on the list by closed intervals, and he takes the intersection of the closed intervals, and then he has some real number which exists by the Cantor intersection theorem, which is different than all these guys. This was the original diagonal argument, and then he just turned that into this, I believe, first, then to this later. But I like this one better, and so should you, and so should all the viewers. So I'll see you next week. No, in 2 hours.